Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys are all doing well. We have a short week this week because Thanksgiving break is coming up. So let's actually just jump into it. The next time I'll see you guys is after Thanksgiving. Just to remind you guys, to make sure, at least to make sure you're aware, I did put up a practice quiz, which by the end of today, you should know everything that you would need to be able to do that quiz. Since we're not having any official quizzes for the rest of the semester, I figured I'd give you guys something to practice on, and which you can do while we're away, just to stay a little bit sharp and brush up on some material. But of course, until then, your homework should keep you pretty busy. I think you have a lot of homework problems, which, you know, I don't mind you doing them in your groups or whatever, but getting through the problems, making sure you understand the concepts, that's all going to be important. Actually, I have some exciting stuff planned today, but of course, before we do that, we have to finish up business from last time. Last time we spoke about conic sections, and not really, not in detail. I left a lot of details in the notes, in the handouts, which you can read at your leisure. But the main thing I wanted to cover in this section was sketching certain conic sections, because they are some objects that students just forget to sketch because they haven't seen them in a while. But I'm sure you guys have come across these guys at some point in your mathematical careers, probably even did a lot with them in high school or in a pre-calculus class. But hyperbolas just don't come up that often in Calc 1, and maybe they didn't come up very often or at all in pre-calc, them as well as exponentials. Everyone knows about circles and parabolas usually, but these guys are less ubiquitous. So I decided to remind you about them because from now on, in the future, being able to sketch curves is going to be important, and being able to sketch conic sections specifically is going to be important. And it's just that students often forget by the time they need to, how do I sketch that again? And so I thought it was just nice to remind you guys. So what we're going to do is we're going to just go through a few of these examples here, which I ask you guys to try on your own, just to make sure that we know how to do it. So, and I put the answers here because I wasn't sure if I wanted to do them in class or not, because again, it's not really Calc 2 material. It's kind of like pre-calc or algebra class, but you know, you can forget a lot over if you haven't done something in a while. So let me see here. So yeah, let's actually go through this. And yeah, for the most part, I am just going to be going through these on my own. But if you guys have any questions or anything like that, don't be afraid to stop me and chime in. As mentioned, I encourage your participation. And of course, if you can turn your cameras on, that would be appreciated. My video is spotlighted, so you won't be recorded. Okay, so identify the conic sections, conic section. Well, it says identify the conic and state its center and sketch it. The answer was it was an ellipse with center 1, -2. How do we have figured it out? Well, if we started, not sure why I'm in blue. If we started 9x squared plus 16y squared minus 18x plus 64y equals 71. By the way, the fact that the x squared and the y squared have different constants is kind of a giveaway that the conic section is not a circle, right? So for a circle, the coefficients of the square terms would have to be the same. Once you see the coefficients of the square terms are different, it's not a circle, it's something else. It could be an ellipse, it could be a hyperbola. It's one of the other conic sections. Of course, if you only have one square, so there was no y squared, then you know it's like a parabola, right? But that's just a giveaway here. So we know it's not going to be a circle. That was never going to be the answer. Possibly an ellipse. But again, the sign of the two square terms being the same also kind of tells you that it's not going to be something like a hyperbola. It might be an ellipse because you're going to have a sum of squares over here. That being said, how we'd go about this is try to complete the square, essentially. So we are going to group the x's. Of course, to complete the square, you need the coefficient of the squared terms to be 1. So I would factor out the common 9 from the x's. I would factor out the common 16 from the y's, which I think 16 goes into 64 4 times. Now what you do is you pretty much complete the square inside the parentheses. There are several ways you can go about this process. Personally, I like the adding and subtracting the constant within the brackets phase. That way I will never forget to actually multiply out by 9 and 16, which sometimes when students take the process of adding the same constant to both sides to create a complete square on one side, they forget that, oh, there was a 9 and a 16 over there that you had to distribute, and they forget to multiply. So just as a check on myself to make sure that I don't forget to do that, rather than add the same constant on both sides, I decide to add the convenient constant and subtract it again immediately inside the parentheses. So we know how to complete the square. We need to add 1/2 the coefficient of the linear term and square it. But then I subtract it again. Right, so I add and subtract the same thing, the thing that I'm supposed to be adding and subtracting. Let me write that in. So here I am going to add 1/2 of -2 squared and subtract it immediately. So I'm adding 0 in a very clever way. And the same thing in the y's. 1/2 of 4 is +2 and square it and subtract it again. Now, the thing is, the first 3 terms, when you do that, will become a complete square automatically, right? And for reasons, again, you covered in pre-calculus, I'm not going to elaborate on this. It's just by taking notice of a pattern. You added the specific constant that would force it to be a complete square when you factor the trinomial. How do you get the complete square? Well, you're going to take x, you're going to take the guy inside the parentheses. So in this case, that was -1. You're going to square it all. Of course, we're left over with a -1 on the outside. So this part here is the complete square. That's where the first 3 terms went. And then the -1 squared is the guy that's left over here. Same thing is going to happen here. I'm going to get y + 2 all squared -4. Now multiply it back out. So it's going to be 9 times x - 1 all squared -9 plus 16 times y + 2 all squared minus, is that a 64 again? Okay, so I have a -9 - 64. What is that, -73? So anyway, let me actually just move them over and add, rather than add 2 negatives. So this would be 71 plus 9 plus 64. So what's that? Why did I write a 6 here? 9. Yeah, so that is 73 plus 71. That's 144. Okay, So how do I get this in the right form to know what it is and how to sketch it? What am I missing?
Wouldn't you need to divide by 9 times 16, which would also be 144? So then you'd have x minus 1 over 16 plus y plus 2 squared over 9.
Right. Well, the better way to think about it is not the 9 and the 16. The 9 and the 16 isn't the main issue here. The main issue is actually the 144. So you definitely want to think of it as divide by the 144. It happens to be 9 times 16, but you don't think of that. You actually remember in the boxes, you know that when you're going for an ellipse, there's going to be a sum of squares. But however, the right side is the number 1 specifically, right? So if you wanted to write it up like an ellipse, you'll notice that the general equation that you would have memorized has the constant 1 on the right side. So it's not that the 9 or the 16 is bothering me, it's actually the 144 that's bothering me. It's coincidental that it happens to be the 9 times the 16. So don't focus on the 9 times the 16, focus on the fact that there's a 144 on that side and I want it to be a 1. So I'm going to divide both sides by 144. So yeah, as you pointed out, 144 is actually 9 times 16. So there's going to be a 16 left over here. And there's going to be a 9 left over there, and there's a 1. And so again, I'm going to write this into that. Because among other things, one lesson that we were reminded of last time is that once you have a set of equations that governs some kind of concept you're aware of, what you want to do is you just want to tweak things to look like that kind of equation so that you can apply the concept, right? So math is about discovering truths and then taking a complicated situation and transforming it into something where you can use a simpler truth to figure it out, right? So reducing complicated problems to previously solved problems. So it's a very traditionally a mathematical way. So the idea is now I've converted into one of those types of equations that we have here. And at this point, it's clear that it's an ellipse. Is it going to stretch more horizontally or vertically?
Horizontally, because
Horizontally, because the bigger base is underneath the x. Okay, so remember how to sketch this. 1 comma minus 2. Okay, so so 1 comma minus 2. So let's put it here. And then we're going to, I don't know if that's kind of level. And then we're going to move 4 units in the x direction. So I'm going to move over here. Notice that, and then move 4 units over there. And of course, since I'm moving 4 units, notice that this is going to be under the 5, and this is going to be under the minus 2. I'm going to move up and down by 3 units in the y direction. Let me actually make this a little bit longer so I can exaggerate this a little bit. Not drawn to scale, obviously. Then I'm going to move up 3 units in the y, down 3 units in the y. Of course, this is going to go across to 1. And this is going to go down to 3 units, so minus 5. So now what happens is you've created that box. And so where these lines hit the box form the vertices. And that's your ellipse. So hopefully that was clear. So there is our ellipse. Center 1, comma -2 stretches 4 units in the x direction from the center on either side, stretches 3 units in the y direction from the center on either side. This creates a box that our ellipse is inscribed in. And I know that I go 4 because underneath here is 4 squared and underneath here is 3 squared, so I go 3. This is also an ellipse. Let's see how this one looks. It already has sort of a complete squared vibe going with it. Again, the 21 on that side is what's bothering me. I'm going to divide by 21. So this leaves us with 21 divides into that, goes 3. And here, 21 divides into that, goes 7. I would think of this as radical 3 squared. Radical 7 squared. So this is an ellipse with center 2, 2. You can see that this one will have a vertical major axis though, and that vertical major axis is somewhere between 2 and 3. So radical 7 is somewhere between 2 and 3. So not drawn to scale, but it's nice to have some sort of relatively speaking. So center is 2, 2. I'm going to move left and right by radical 3. Radical 3 is a little bit less than 2, so I'm not quite going to get to the y-axis. So this is going to be over 2 minus radical 3. This is going to be over 2 plus radical 3. And in the y direction, I'm going to go up and down by radical 7. So here, this is going to be 2 plus rad 7. Down here, this is going to be 2 minus rad 7. So this creates a box. That's our ellipse. Yeah, as I mentioned to you guys, like I'm not gonna ever ask you about foci and that stuff, so you can actually forget about this or the equations of this. You'll know how to find the asymptotes, and if you had to, you could find the equations of them, but I'm never actually gonna ask you about that. So you can actually ignore that if you want. I mean, even what I'm doing so far is actually a little bit more detail than you would have to actually produce. When you're going to need this, it's more detail than you're going to have to produce. But if you know it in this much detail, not even as much as you would need to sketch with in Calc 1 with concavity and worrying about all that, but just know how to basically sketch an ellipse. It's going to be very important. You're going to need to know how to sketch this in like 3 dimensions in like weird situations. So if you don't even know how to do it in the flat 2D plane, you're going to be in trouble. Right? So, okay, what about this guy? So here I have 4y squared minus x squared. So I noticed 2 things. The sign of the squares, they're on the same side and there are different signs, which means it's not a circle and it's not an ellipse. Right? Could be a degenerate conic. However, we're not dealing with those in this class. I don't know where this is coming from. So it has to be hyperbola is what I'm going to guess. And initially, it looks like it might be going in the y direction. However, I don't know what the constant on the other side is going to be, so I'm not going to make any predictions right now. What we would want to do, again, is group the x's and y's. Move the constant to the other side. So now what we want to do is factor out the coefficient of the squared term. Going to add and subtract half the coefficient of the linear term. First part is a complete square. Come over here, and so that's 4 times y minus 3 squared minus 4 times 9 is what, 36? So I have minus 36 plus 1, which is minus 35. Move it to the other side, you're going to get plus 35, which means over here, we're going to get a plus 4. Now, assuming I did all that correctly, I want to divide both sides by 4. So this leads us to y minus 3 squared over 1 squared minus x plus 1 squared over 2 squared equals 1. So we know that's a hyperbola. Since I know that the y is the positive one, it opens north-south. How would we sketch this? So center 3 comma minus 1. Okay, so whatever, let's put it 3 here, minus 1 there. That's the center. You're going to play the same game. Move left and right by the x, the denominator and the x. So I'm going to move over by 2. Move over by 2. So this actually brings me up to 5. This actually brings me down to 1. I'm going to move up and down by the y, which is 1. So it's literally going to go up to here and down here. That's going to give me a -2. This is going to create a box. And from that box, I'm going to now generate asymptotes going through the diagonals. I'm drawing these in broken lines because they're just the skeleton. They're not really a part of the graph. They're just going to be a guide to sketch the graph. Now, because the y was the positive square, it's going to open in the y direction. So it's going to, so the vertex is going to be on the vertical axis, and it's going to open like so.
Wouldn't 3 be the y coordinate of the center?
Oh yeah, I wrote it on the other side. Geez, you could have warned me when I wrote it up here. Yeah, these are flipped. Oh God. Okay, so it's still, can I salvage this? So I'm like a nefarious scientist who's like doctoring his results to kind of like fit what the story he wants. Okay, so let's call I need the x to be -1 and the y to be 3. So undo. So I need this, it's actually -1, 3. So it's gonna look over here, right here. Where this is at 3. How far am I supposed to extend in the y direction? Not that far. Supposed to extend by 1. So this should be on the axis. At the level 3, and this is at the level -1. From the x, I should be extending down 2. Okay, so I actually don't want the x-axis here. I want the x-axis like here. Where this is at the level of like -1. Okay. I think that fixes it. Okay, does that fit? Things are going so well. Let's see, do I have anything else? Oh yeah, rotation of axes, ignore that. We don't need anything that complicated for the future. Yeah, that's our hyperbola. In fact, I think we did yeah, so this was actually the answer. So that looks better. Oh, I think I actually extended the box in the wrong way too. Let me annotate this instead of going up. So this should be 2. And this should be length 1. So the axis was in the right place before. 2 in the X direction. 1 in the Y direction. All right, so that's that. So the only thing I wanted to cover in this section is how to sketch these guys, because it's going to be important at some point, and it's the thing that most people forget how to sketch. That being said, all forms of sketching curves you should know. Like I said, you're not going to sketch things in any level of detail like you did in Calc 1, where you had to find concavity and all that stuff. You're going to do concavity tests, but you're not going to diagrammatically demonstrate it. So you are going to have to do sketches, or at least that's the better way to do it. I don't know if you're going to be required, like, oh, you have to do a sketch or you're going to lose points. But knowing how to sketch things in 3 dimensions is definitely going to be useful. Your work will be 2 to 4 times harder if you decide to, you know, I'm not going to learn to sketch. So don't fear it, lean into it. Okay, so that's all I want from this section. So review what I have for parabolas and circles. If you think you've forgotten that, I'm going to assume you know that stuff anyway. But that's it for the conics sections section. So now we are going to move on to the next thing, which again, it's all still going to be an intro, but it should be fun. We're going to do 3D stuff, which is going to be very exciting. I'm going to introduce you to the new world that you will be getting accustomed to. I'm going to leave this guy hanging out here because why not? So last phase of the class, what we're going to be wrapping up with is we're going to be talking about some stuff in 3 dimensions, which should be cool. We're going to talk about 3-dimensional space. We're also going to talk about vectors and 2 things called the dot product and the cross product. Hopefully I can finish all that. Quite ambitious. In like, how many classes do we have after this? 3? I might also do a section on sketching surfaces, although that probably won't be an official lecture or something like that, but I'll see how it goes. I'm thinking about it. Okay, but for now, we're going to talk about 3D space. So again, very introductory, but going to take some imagination, some sketching ability. Let's jump into it. So we're going into chapter 12, where we're going to introduce the 3-dimensional coordinate systems. Now, that's what your textbook calls the section, but it's not actually. It only talks about one coordinate system, really, which is the rectangular coordinate system, the Cartesian coordinate system, which is a generalization of the coordinate system that you had in 2D up until last class. So, I mean, here I say, recall, load, record, or locate points. We already did this, right? So essentially, if I want to say record the point 1, 2, we know how to do that. Well, you move 1 on the X, move 2 on the Y, and essentially you create a rectangle to locate that point, okay? We're going to do the same thing, except we're going to be doing it in 3 dimensions. So I'm going to teach you the coordinate system that you're going to, one of the main coordinate systems that you'll be using in 3 dimensions, as well as just introduce 3-dimensional space more generally. So let's actually get into it. How do you even sketch 3 dimensions? We will sketch it like so. We have 3 axes now. So we're not going to keep our attention on 2 things. We're going to keep our attention on 3 things. This is how we sketch it. You draw a vertical line, draw 2 lines going like so. These guys represent your new axes. Now, who are these guys? This guy here is your x-axis. This guy here is your y-axis. This guy is the new z-axis. This guy represents the 3rd dimension, the 3rd coordinate. We've been looking at the x and y-axis. You can think of those as like analogous to length and width. Now we're adding a component of height. Now, to be fully transparent. There are other ways that you can draw this. I see this one fairly often as well, where they draw the Z coming out here. But a lot of calculus books rather use the first version that I drew. If I see stuff like the one I just drew here, it tends to be in like a physics book, and it's very rare to see them in a calculus book. But in all of Stewart's textbooks, he draws that with this orientation. And so you should be aware, I'm going to assume that this is the orientation you're sketching it in. And you should be aware that whenever I'm discussing something, this is the orientation I am thinking about. So there are going to be times when I might say something is to the left or to the right or above or below something. And it's very important that you recognize that I'm thinking of the x-axis as going here, the y-axis is going there, the z-axis is going there. So if I say something like it's below the xy plane, you know that it should be towards the bottom of your diagram, right? For example. So this is the orientation we're going to use. So essentially what has been happening for your whole life until now, we've essentially been looking, long, beautiful eyelashes here. We've essentially been looking down at the XY plane like so, until now. But now it's time for the red pill. It's time for you to realize that the world is a lot bigger than the XY plane. It's also time for you to realize that there are a lot of things that you thought were true, that you thought you knew, that it just ain't so. You've been in the matrix for a long time, and it's about time we get out of it. So you're going to realize that in 3 dimensions, a lot of things are different. A lot of things work differently, and life isn't exactly as you know it. That being said, conceptually speaking, the jump from 2 dimensions to 3 dimensions is the hardest jump to make. Once you get very comfortable with working in 3 dimensions, it's going to actually be a lot easier to work in 4, 5, 6, 7, infinite number of dimensions, really. Once you really learn how things operate in 3D, you kind of can generalize that to ND very well and very efficiently. However, that jump from 2D to 3D is actually, literally, it's like a matrix experience. So you're going to realize, what? I thought my whole life that this was, nope, it's not. And we're going to see some examples of that here. Boom, boom, boom. Here, of course, this would be the negative x-axis here, which you don't always draw these, but I'm just showing you how it would look. Here, that's the negative z-axis. Okay, so this is the world now. Okay, especially when we're doing 3D. Now, how can we locate points in 3D? It's actually going to be very similar in the rectangular coordinate system. So here's my x, here's my y, here's my z. Locate points in rectangular coordinate system. There are going to be 3 main coordinate systems you're going to learn about. One that takes polar coordinates into account, and there's going to be another one that takes a whole other set of coordinate rules called spherical coordinates, which they're all very important. So essentially, you kind of play the same game that you did in 2D. What you're going to do is you're going to find all these coordinates on each of the individual axes. You are going to notice that this is always written in the convention is x, y, and z components respectively. So it means that there's a 1 on the x, a 2 on the y, and a 3 on the z. You pretty much start out by writing them down. 1 on the x, 2 on the y, just like before. Then what you're going to do is, again, you're going to create that rectangle. But of course, that's going to be in 3D. Now it's going to be on the floor. It's going to be in the xy plane. And then what you're going to do is you're going to find 3 on the z. And again, you can create rectangles over here. You can create a rectangle over here. And essentially what you now create is a 3-dimensional rectangle or a box, right? And again, finally, what you're going to do, it's going to be the point that's opposite the origin. As always, it's going to be that corner. So that coordinate is going to be here. This point hovering above, so this is going to be the coordinate 1, 2, 3. This is the point hovering above 1, 2 in the xy plane. More specifically now, 1, 2, 0. So everything you've learned up until this point, there was always a comma 0 on every coordinate that you've ever seen before. Maybe a comma 0, 0, 0, 0, depending on what context you want to take this to. But that is going to be how we locate a point. Pretty much draw a box instead of a rectangle. If you're in 4 dimensions, it's going to be like this hyper box or this hypercube, which case we can't even visualize it anymore. But yeah, that's how you locate coordinates. Now, let's get our bearings. Again, we're kind of used to how to look at a 2D world, but how do you look at a 3D world? Well, if we're physically in person, I would normally do this thing where I walk up to a corner in the room and I show people how the 3D world is going to be. But of course, we're online, so we have to make do with pictures. So essentially, I want you to think of the room you're in to kind of figure out how the 3D space is going to operate and how we're going to label things. Okay, so imagine that you're just standing in the room. This is you. You gain some weight, and you're looking at the corner. Okay, so you're standing, you're facing a corner of your room. What you can do is just imagine that the corner on the floor, the edge of the floor, that's your origin. And you can imagine that the crease of the floor, the crease of where the wall meets the floor, running along it towards your left, here is going to be your x-axis. And if you imagine moving here, that's going to be your y-axis running against the wall. The floor that you're standing on, that is the xy plane. So in other words, you have these guys, right? So you have what's called the xy plane, because that is the plane that's spanned by the x and y axis. You have the yz plane. That is the plane that's spanned by the y and the z axis. And then you have the xz plane. That is the plane spanned by the x and z axis. And for all intents and purposes, you can think of these as like walls where they're infinitely thin, right? So they're kind of like sheets. They're 2 dimensions only, they have no thickness. So the xz plane, the yz plane, and the xy plane, these guys are called coordinate planes, right? So just kind of the same way you can call the xy axis the coordinate axes, right? They all have equations that pretty much say the other guy is 0. So just like how the x-axis is the equation y equals 0, and the y-axis is the equation x equals 0, these are also like that. So the xz plane can be thought of as the plane x equals 0. The xz plane can be thought of as the plane y equals 0. Every point along that wall, the y coordinate is going to be 0. The xz plane is the coordinate, has an equation z equals 0. So everywhere where z equals 0 will be the floor, right? So this is the xy plane. Okay. So, I mean, at this point, in terms of space or how things are being called, it's not really something to understand. These are just the conventions. Think of the z as going up, the x running off like that, the y running off like that. And the room we're standing in is the first octant, as it will called. You'll notice here that since we're in 3 dimensions, you can kind of see that there's like a room back here, right? There's also a room behind that wall. There's probably also a room below the floor. I mean, just where you're seeing the positive axis isn't all of space. That's just one part of space. Just in the same way that the x-axis and the x-axis and the y-axis, it actually split 2-dimensional space into 4 quadrants. You'll notice that in 3 dimensions, these walls that I just mentioned actually splits space, 3-dimensional space, into 8 sections, right? And these 8, they're called octants. Octo for 8, right? So if you want to think of the more expanded universe or the more expanded environment, it's probably better to not even just think of being in a room, but to rather think of being in like a 2-story building, right? So here I'm just drawing a little bit more about what it would look like, and for you to visually see that, oh, there's stuff behind all of these things, right? So you can kind of imagine like that you're in a 2-story building. So again, here's you standing in a room looking at the wall, right? You are standing on the XY plane, at least a part of the XY plane where the X and Y coordinates are positive. Of course, there are going to be parts where the X is positive, but the Y is negative. They're both negative, where the X is negative and the Y is positive, etc. Right? Now, the room, so here is going to be the YZ plane, which is going to be the wall to your right. The XZ plane is going to be the wall to your left. And the XY plane is the floor you're standing on, but you're on the 2nd story. The room behind the wall to your right, this is what we call the 2nd octant. Then if you are standing in that room facing in the same direction, the room behind the purple wall over here, that's what we call the 3rd octant. And of course, the room behind the left wall in the 1st octant is going to be the 4th octant. So you label them counterclockwise just as normal. So if you were just looking down in the bird's eye view of how you normally looked at the quadrants, they're labeled the same way, going counterclockwise. And then you start counting again from 5 in the floor below. So the room below you, that is what's called the 5th octant. And then behind the wall over here, that's the 6th octant. Then behind that wall over there, that's the 7th octant. And then you come over here, that's the 8th octant. However, the 1st octant is the most important. And usually in your calculus book, it's going to talk about, oh, there's something in the 1st octant, right? So they usually mention the 1st octant by name. They don't normally name the other octants, but just for your education. So that's what that is. So that's 3D space for you. Okay. So far, any questions?
No, I think we're good.
Okay, so so far everyone's with me. Okay, so hopefully you're kind of understanding how things are set up, right? So we're going into a 3D world here. So finally, the math is going to get interesting and a lot more realistic. So now let's talk about objects in 3D space. Okay, so we're going to talk about how things really look. Okay, so I'm going to actually sketch these objects. So let's look at x equals 1. Now, up until this point, if someone were to say, oh, what is x equals 1? What would you have said then? What does that look like? What would be the sketch of such a thing? Prior to this class, what would your answer have been? I say x equals 1. What's that? We actually sketched that last class, actually.
A vertical line.
It's just a vertical line, right? So that was when you had the blue pill. Now it turns out x equals 1 is not the equation of a line. It is actually something else entirely. So yes, I understand your whole life you thought x equals 1 was a line. This is not, it's not correct, unfortunately. Okay, so in the bird's eye view, x equals 1. What is that, right? So x equals 1 was just this line that you guys knew about that was in the xy plane, and it was, for what you thought, was vertical, meaning it was running parallel to the y-axis, right? And yeah, any coordinate that you picked on here, the x coordinate was actually 1. But here's something else that you'll notice. If you actually vertically rose up directly over that line, guess what your x coordinate would be? It would still be 1. So if you start vertically rising directly up at a 90-degree angle to the xy plane, your x coordinate would not change because you're still hovering over the same line. So it turns out x equals 1 actually creates what we call a plane. And so this is like an infinite wall. It's very straight. So you can think of it as consisting of an infinite number of lines. Of course, it extends in all directions. So it keeps going this way, keeps going that way, keeps going that way, keeps going this way. But it's actually a plane. In the same way, that we call the coordinate planes. They had their equations, right? So x equals 0 is not a line, right? So before we just thought, oh, x equals 0, that's the y-axis, right? Well, it's not. It's this entire infinite plane, right? So that is what that object looks like. Similarly, we can talk about these graphs. So now, obviously, you're going to realize that let me move this on the other screen because I'm all zoomed in here. I'm gonna get myself confused and mess something up. Probably actually move this one below. Give me a second. Just reorganizing the structure here a little bit. Okay. Y equals 2 has a very similar, y equals -2 has a very similar story. So again, we draw the, still in blue. So again, we draw the axes here. That's your x, that's your y, that's your z. Of course, the negative z keeps going down, negative x keeps going that way, negative y keeps going that way. Of course, y equals -2. That's going to be on the negative side. So -2 is over here. And looking down from a bird's eye view, what we would have seen is a horizontal line. However, if we move directly up and down from that horizontal line, the same thing is going to hold true. So there's actually a wall, an infinite wall, that is behind this guy. Actually, I wanted to look. It's behind. So that's actually behind the XZ plane. So I could say something here. It's like, oh, it's a plane passing through y equals -2 to the left of the XZ plane or behind the XZ plane. I could describe it as those things. And I could just say, well, it's parallel. It's a plane that's parallel to the XZ plane. So y equals a constant is going to be parallel to the XZ plane. X equals a constant is going to be parallel to the YZ plane, etc. If we look at something like Z equals a constant, we can sketch that as well. This continues to go there, this continues to go there, this continues to go there. So here is 3. And now it's like, well, let me move that down. Now it's like, again, you have this infinite sheet moving in all directions, but it's parallel to the, use a different color. Maybe green. Infinite sheet. That's parallel to the parallel to XY plane. Extending in all directions. So it's actually a sheet. So equations that you would normally look at as lines, they're actually planes. They've actually been planes this whole time. When you saw x equals 1 as a line, what you actually saw was just its projection in the 2D plane. It was actually much bigger than you realized. A lot more was going on than you realized before. And yeah, again, y equals x. You thought of that as a line. It's actually not a line. It's actually a plane. This one's going to be a little bit harder to sketch, though. I don't know. This is where y equals x. Coming back that way. It's like slices through the z. Okay, so those guys are all planes. Okay. Right, so that's just one of the way in which you haven't been told the whole story, or it was never important, you know? It's just like when you were a baby, they told you, you can't subtract a bigger number from a smaller number. Then you learn about negative numbers and you're like, you lied to me this whole time? Well, that was a lie. Then you're going like, you got a little bit older and they tell you, oh, x squared plus 1 equals 0. It has no solution. Then you learned about complex numbers and you're like, so that was a lie? Okay, yeah. Math is going to get a lot more honest, a lot more real from now on. Well, we'll see. Let's keep going. So in light of all that, what do you think this is? X squared plus y squared equals 1.
I bet it's a sphere.
I think it's a cylinder.
Cylinder. Right, so yes, as we've all thought, x squared plus y squared equals 1 has always been a circle of radius 1. But now you know that that's really just a circle of an image that was projected on a floor. However, if I were to move directly above that circle or directly below that circle, I would still have the coordinates of the x and y behave like that. So it would end up looking like that. It's actually a cylinder. We are going to talk about spheres.
Oops.
But this isn't actually a sphere. No, it's fine. It was a good guess. So now, yeah, you realize. Right. So what our x squared plus y squared equals 1 used to be was this circle in the xy plane that passed through x1, passed through y1, passed through x equals -1, passed through y equals -1 as well. But now you can move up and down and you're not changing the x and y coordinate. You're just varying the z coordinate. So now you can actually move directly up or down above that and nothing is, and your x and y can maintain the same relationship. Somewhere that looks like an ellipse to me. And again, it keeps extending up forever and down forever. And looks like a circle when you look from above. But yeah, it's actually a cylinder. Okay, so yeah, x squared plus y squared. You thought that was a circle? No, it's actually a cylinder, which is a very different thing from a circle. And so it's actually hollow inside. It is still a two-dimensional figure. So technically, by our definition, a circle was a one-dimensional figure before, but it's actually not. It's actually a two-dimensional figure. I don't know why I can't move that up. I will do it later. So now let's talk about spheres. To talk about sphere, we first have to know the notion of distance. Notion of distance is very analogous. So this is one of the things that do generalize nicely, is that the distance formula looks pretty much the same. You just take the difference in each coordinate, you square it, you add them all together, you take the square root. And that's because when you're finding the distance between 2 points, right? So these points you can project to 2 points down in the xy plane. This here, you can find that distance being x2 minus x1 squared plus y2 minus y1 plus y2 minus y1 squared by 2D distance formula. So Pythagoras' theorem. Which means the idea is if you want to find the distance d between 2 points in 3 space, this line gets projected up to here, right? So this is the square root of x2 minus x1 squared plus y2 minus y1 squared. And now this distance here is just z2 minus z1, right? So this part here is x2 comma y2 comma z2. Then this point here is going to be x1 comma y1 comma z1. Then now when you take this length and that length, the sum of the squares must be equal to d squared. So by Pythagoras again, d equals that. Right? So Pythagoras' theorem thankfully still works in 3 dimensions. Now, when you want to talk about a sphere, how can you describe a sphere? Well, it's the set of all points that is equidistant from a single point, right? Same way how you describe a circle in 3D, in 2D. Back in 2D, what was a circle? It's where you pick a point and then you find all things that are the same distance away from that point. That distance was called a radius. Take the same guy in 3D, and that's what a sphere is. So essentially what you want is you want the set of all points x, y, z that are the same distance r from some point h comma k comma l, which means r must be the square root of the distance formula. And so r squared is just going to be the sum of these squares here. So it turns out the equation of a sphere, you need all variables present because you have to stretch in all directions. Right, so you can't just have x and y going through changes. So like here, we only had x and y present, which means no one's telling the z that the z has to conform to a certain distance. So there's no way it could be a sphere. In fact, this is going to be a general thing. Anything in 3D that has only 2 variables in it is going to be a cylinder, some form of cylinder. And it doesn't have to be a circular cylinder like this. It's just a general cylinder. This includes planes, technically. Those are kind of cylinders that are opened up. But yeah, guys with only 2 variables in their equation, these guys are what we call cylinders. The most famous cylinder is the circular cylinder. Yeah, and now, you can do what we were doing just before with completing the square, which is why I went over conic sections, because you can think of a sphere as just a circle. If you slice it through the radius, the outline is always going to be a circle. So if you know how to draw a circle, technically you would know how to draw a sphere. So what you can do here is show that this is the equation of a sphere. How would you do that? Well, by completing the square, just as we've always done. So what you would do is you would move everything to one side. You would group the x's, group the y's, group the z's. You would add and subtract. Well, at this point, you can add this to both sides because it's not gonna. So I want to add something to the x part to make it a complete square. I want to add something to the y part to make it a complete square. What is the thing I need for the x? Half the coefficient of x squared. Add that to both sides. What is the thing I need for the y? Half the coefficient of y squared. Add that to both sides. So here I would get x minus 2 all squared plus y plus 1 all squared plus z minus 0 all squared equals 5. So that is a sphere. Radius radical 5, center 2 minus 1, 0. Okay, and you know that just by matching it up with this equation right here. So spheres have this form, right? So it's like a generalized circle. You now have a z component squared attached to it. Okay, now let's talk about regions in three-dimensional space. Is this thing now working? Still not working, I don't know why. And I believe, yeah, this is the last thing we're going to talk about. Okay, regions. So now, again, 2D is often referred to as R2. So how do you sketch a region in 2D? Let's just remind ourselves. Yeah, with the x and the y, if I wanted you to sketch y less than or equal to x, what you first do is you imagine the inequality as an equality, and you actually sketch the line y equals x. And now you shade the region where the y coordinate is less than or equal to the x coordinate. So you can pick a random point, say here. You know it splits space into two regions. There's a part above the line and a part below the line. Pick a random point. This would be like 0, minus 1. Is the y coordinate less than or equal to the x coordinate? Yes, which means you want this region down here. Okay. Similarly, if I wanted y strictly less than x in R2, we can represent that essentially by the same thing, except we draw a broken line. Right, so it's like. So it's everything below that line, not including that line. In this case, we include the line. Okay, so that's region in 2D. Nothing new, nothing special, but I just want you to know what we talk about when we say region. Okay, so now we're going to do regions in 3D. Okay, so for example, sketch the region x squared plus y squared plus z squared less than or equal to 1 in the first octant, right? So there's that phrase in the first octant again. Okay, so what is this guy going to look like? What do you guys think? first you sketch the equality, right? That's how you did it in 2D, right? So if I were to sketch x squared plus y squared plus z squared equals to 1, what would that be?
That's the sphere, right?
That's a sphere. Now, I don't want the whole sphere. I only want the sphere in the part of the sphere in the first octant, right? So, however, like always, I want to sketch the entire thing and then highlight the part that I actually care about. So let me draw a sphere in blue. What we're going to do is you pretty much draw a circle. And you can draw like the equator. Right? Looks like a little Death Star. And then now what you can do now is you can cut out the part that is in the first octant. So it's actually, so where the equator hits the x, it's going to be like that. Where the equator hits the y, be like that. It's going to slice off here. So this is my region here. Make it a yeah, so that's it. It's part of that sphere. So this is the part of the sphere in the first octant where the x, y, and z coordinates are all positive. So it's actually 1/8 of a. You can think of it as 1/8 of a solid ball. So it all points inside as well because it's all x squared plus y squared plus z squared less than 1. So it also has it would include the origin, etc. And we could describe this in the cylindrical coordinate system. This would be, of course, r goes from 0 to 1. Your theta would go from 0 to pi over 2. And your z would go from, well, 0 up to the square root of 1 minus r squared. This is cylindrical. In rectangular, you could describe this region as x goes from 0 to 1. Your y goes from 0 to the square root of 1 minus x squared. Your z goes from 0 to the square root of 1 minus x squared minus y squared. And yeah. But yeah, that's the picture. Is there another one? Okay. So just one more. I know we're out of time, but just bear with me. I want to do this one. Just this last sketch, I want to sketch the region. How are you guys feeling? You want to take a crack at it in groups, or do you want me to just go over it? I can give you guys a few minutes, like 3 minutes or something, and then we come back.
It'd probably just be easiest if you did
it. Okay. Can you give me some ideas of what you think it would look like, though?
It'd be like a sphere, except there's a hollow void in the middle.
Okay. And what's the shape of that hollow void?
It would be, that itself would be a sphere with radius 1, centered at the origin.
Right, so there are two spheres. Okay, all right, so we're getting somewhere. All right, so let's say there's one sphere. Right. And there's actually another sphere inside of that one. So that outer sphere has radius 2, and there's an inner sphere with radius 1. Okay, now, do we want the whole sphere? What part of the sphere do we want? Okay, try to use the language that we've spoken about. So it's this guy, which, yes, that's a sphere inside of another sphere. But then it says for y less than or equal to 0 and for z greater than or equal to 0. So kind of tell me positionally where this thing is.
It's in the negative y direction and in the positive z direction. And there are no bounds for x.
Okay, tell me in terms of planes. If you were to describe to me in terms of coordinate planes, how do you describe it? You know, like back in 2D, if I were to ask you, what does it mean for a graph to be positive? You would say to me something like, oh, that means the graph is above the x-axis. Use
okay.
similar language, but with planes.
So there'd be two different planes. So there's positive z, negative y, and positive x. And then positive
well,
z.
These aren't really planes. So you have to describe like the xz plane or the xy plane or something like that.
Was I not doing that?
No, you said positive z, positive y, negative x. Like to describe the coordinate planes, you have to say two variables, right? You can't just define a plane by one variable. At least you can't define a coordinate plane by one variable.
Could we describe it in octants instead?
Sure.
Would it be the third and fourth octants?
Yes, it would be in the third and the fourth octant. Right. Another way you can describe it, it is above the xy plane and behind the xz plane is another way, right? Both are fine. I will say though, in general, like I said, I told you where all the octants are, but a lot of people don't even mention them. So when you go to the next class, a lot of your classmates might not even know where the third octant is. So they better know it in terms of the coordinate planes. And probably if you're seeing language used in your textbook would define it in terms of coordinate planes. So if it wanted to say something was in the third and fourth octant, it would say, oh, it's behind the xz plane above the xy plane, as opposed to using the numbered octants. I don't know for what reason, but that's just how it is. So that being said, I just want to carve out the part of this object that fits that description, which means I need to slice the little sphere where it would meet this thing in the XZ plane. Of course, this guy here also, I'm going to slice this where that meets the XZ plane. Okay, so this is like the face of the thing that I'm seeing. Now it extends behind, right? It extends back here. And there's a part of it like here. I think this one's kind of messed up. Oh. Okay, I wanted this guy to come down here. I know how I'm gonna fix that spot. I'll fix it later. I know what that's supposed to look like, but that's the object here.
Could you write down what you said about it being behind the XZ plane or whichever one it was?
So this is behind. This is behind the XZ plane and above XY plane. Or you can say it's in octants 3 and 4. But that's going to be the guy. Of course, I can embezzle that a little bit, but you can start by just drawing the overall sketch and then slicing out what you want. Just as before, you draw in 2D, you drew the equations, and then you shaded what you want. Same sort of thing. You draw the sphere, which is the equation, and then you cut off the parts that you don't want, leave the parts that you do want. So yeah, that's it. We will stop right there. That's 3D. So next time we'll actually talk about vectors, because like I said, things don't work in 3D the way they worked in 2D. Things that you thought were lines are really planes, etc. And it turns out that a better way to describe a lot of things in higher dimensional space is using vectors. So we're going to talk about vectors next time. But for now, we will stop right there. Thank you for your attention. And I will see you guys after Thanksgiving. Have a good Thanksgiving break. And I'll see you. If I need to say anything, I'll say it on Jupiter. I don't remember if I had any announcements. I felt like I did, but we can stop there. Okay, so that is all she wrote. Good night, everyone. Again, have a good night. And I will see you guys in the next one. Be safe. Ciao.